Welcome to Introduction to Chemical Equilibrium. We'll break this topic down into two parts where we first discuss what equilibrium actually is and what it means for a system to be at equilibrium. And in a separate video, we will discuss what's called Le Chatelier's principle, which talks about ways to shift or change equilibrium. We're going to start by considering a reaction where we are reacting sulfur dioxide gas and oxygen gas. What could potentially happen in an enclosed container like this is your oxygen molecules, your O2s, can split in half, and you can have each of these oxygen atoms potentially end up on separate molecules of SO2, and you form a product called SO3. So this SO3 product that you could potentially form comes together in a reaction that says 2 SO2s plus 1 O2 makes 2 SO3s. And you can see that reaction drawn out for you. Oops. You can see that reaction drawn out for you right here. And keep in mind, because of balancing, that's why we've got some of the coefficients that we do. So we start with 2 sulfurs, we end with 2 sulfurs. We have 1, 2, 3, 4, 5, 6 oxygens going in and 6 oxygens coming out. So this is what we actually consider to be a forward reaction, because SO3 can actually decompose back down into SO2 and O2. So you can actually have a decomposition reaction here where the SO3 is breaking into those initial reactants. So this is what we call a reversible reaction, which we talked a little bit about with energy diagrams. In this case, we have a forward and a reverse reaction occurring. So my forward reaction again is my SO2s plus my O2s making SO3s. My reverse reaction is the decomposition of that SO3 into SO2s and O2s. We can actually write these together, so if you write all this out all the time, you might have seen this double arrow notation before. So I can just write this as 2SO2 plus O2, and I can write this 2-direction arrow like this, 2SO3. Is it okay to do this? You might be wondering. Yeah, this means the same thing. You just have to kind of keep in mind we'll be referring to forward and reverse reactions, and it can get a little bit confusing. So we like to make sure that we're, in the same place as everybody else when we're all writing things in the same direction. So a reversible reaction can come to what's called a chemical equilibrium. So in reality, we don't really have all SO2s and O2s. We don't have all SO3s. In reality, we really have a mixture where we're going to have some O2s and SO2s and some SO3s. So in reality, we actually have this system at equilibrium where we don't just have SO2 and O2. We don't just have SO3. We have a mixture of them. What it actually means for a system to be a chemical equilibrium is that we have 2 opposing processes going on, and they're happening at an equal rate. So what this actually means in this diagram is the forward reaction. So the reaction of SO2 and SO3 turning in SO2 and O2 turning into SO3 occurs at the same rate that SO3 decomposes back down into those initial reactants. So what it means to be at equilibrium is we have 2 opposing reactions. But the rate of each of these reactions is the same. So the rate of the forward reaction equals the rate of the reverse reaction. There are other types of equilibrium. We will discuss physical equilibrium as well. These are also just opposing processes that are happening at the same rate. This means some pretty important things in terms of concentration. So if we look at a concentration graph, and you really don't need exact numbers in your sheet so much as you want to be able to kind of draw a sketch of these. So if on my concentration graph right here, I imagine that I started with SO2 and O2. And as time went by, so I have time on my x-axis, as time is going by, my concentration of SO2 and SO3 are decreasing. The reason they are decreasing is they're reacting and forming SO3, which is increasing in concentration. Now, very often when we look at a graph, one of the things we care the most about is where the graph intersects. With equilibrium, this actually is not the case. What happens that's of interest in this graph occurs right here. This is when the system is at equilibrium. So if you're sketching a graph of a system at equilibrium, what's really important is where these lines right here are leveling out. And what those lines leveling out is telling me that it's telling me that I have reached constant concentration. So if I start with SO2 and O2 only, what I had occurring was that forward reaction that we discussed, SO2 plus O2 making SO3. As the concentration of the SO2 and O2 are decreasing, the concentration of the SO3 is increasing as the reaction proceeds. So at the end of this, what we end up with is SO2 having a reaction, or a concentration, of 2 molar. O2 has a concentration of 1 molar. And SO3 has a concentration of 8 molar. What you'll notice about these numbers is they are not equal to each other, and that's okay. These concentrations do not need to be the same as each other. There's no real necessarily significance to that. What they do need to be in order to be at equilibrium is constant. If we started instead with SO3, so say originally we wanted to run the reverse reaction as our first reaction. SO3 is going to break down into SO2 and O2. What you're going to notice here, the lines don't happen to cross just because SO3 is always greater in concentration. It doesn't go down as low as the other ones. We still are ending up at equilibrium. And we know that where those lines are straight, and that's telling us our concentrations are constant. So here we really started with our reverse reaction. And so we started with our SO3, it broke down into SO2 and O2. What we will notice from this graph is our concentration of O2 still ends up at 1 molar. Our concentration of SO2 still ends up at 2 molar. And our concentration of SO3 still ends up at 8 molar. So in this particular system, those concentrations ended up in the same place that they did no matter which way we started. What's important is that once we reached equilibrium, that concentrations are constant. So again, what's really important to notice about the concentrations of each component is that they become constant at equilibrium. They're not equal to each other necessarily. It could be, but not in this system, and not in many systems, but they are constant in equilibrium. Have these reactions stopped? No, they have not. SO2 and O2 continue to react and form SO3, and SO3 continues to decompose back into O2. What's important at the end of the day to walk away with is the fact that at equilibrium, concentrations are constant. Reactions are still occurring. This is a vibrant system. This is a dynamic system where something is still happening. So my equilibrium concentrations are going to be constant, but these concentrations are not going to be equal to each other. There are systems where they may turn up equal, but definitionally they do not need to be. Show you a little animation of this. In this particular system right here, we have NO2. Two NO2s can react with each other and form N2O4, which can break back down into two NO2s. I like this animation because as we go forward, actually hit continue on this, we let these move around. We can see that this is a dynamic system where these two reactions can occur. So we can have formation, or we can have them break apart, decomposition. Now, if we take a moment and we count the number of molecules of each kind. So the smaller molecules, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 NO2s. We have 1, 2, 2, 3, 4. No matter how long we run this system, I guess I did that sort of backwards, sorry. So if we begin this again, what we'll see is that anytime the system is considered to be at equilibrium, we always have 1, 2, 3, 4 of the large molecules, the N2O4s, and we'll always have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of the smaller molecules. So I can continue to run this. It'll let me. And as I'm playing this, what you're going to see is every time two of the N2O2s get together, somewhere else another N2O4 breaks down at the same rate, thus making it so that any given time that I start this, so if I even go back to the beginning, I'm going to notice I have that same number. As I'm running this, I always have those same equilibrium concentrations. NO2 I always have 12, and N2O4 I always have 4. What I like to leave you with as a little helpful saying is this. At equilibrium, concentrations are constant. Rates are equal. So in any system that is at equilibrium, two processes that are occurring that oppose one another are occurring at equal rates. The concentrations of any of your reactants and products are going to remain constant. The reactions still continue, but because they're continuing at equal rates, the concentrations of each of the reactants and products from the forward and reverse reactants, in other words, the concentration of each species, remains constant. The concentrations will not necessarily be equal to each other.